Hello and welcome to High Availability Lessons Learned here at Monster Scale Summit. My name is Preuveneers and I am the Director of Solution Architecture here at ScyllaDB. I've got 22 years worth of databases and NoSQL experience, and I've been in this industry for quite some time. So I spend a lot of time snowboarding with the guitars and also learning Kung Fu when I'm not thinking about databases. So what is this talk about? Well, there is a lot of ScyllaDB that is directed towards fixing issues with high availability and resilience. We've learned a lot whilst building this distributed architecture, and we wanted to let you in on some of the details from the core architecture through query reliability, topology requirements, and your choice of load balancing algorithms through our newly strongly consistent raft metadata capability. This is a quick run through of how to increase your resilience. So why is HA important? What does it mean for your business? Well, despite all of the safeguards that are put in place, even things like this can happen. Less than an hour after midnight on Wednesday, March the 10th in 2021, in the city of Strasbourg, a fire began in a room at the data center of OVH Cloud. It's a popular French cloud provider. Within hours, the fire had been contained, but not before wreaking quite a lot of havoc. The fire nearly entirely destroyed the building, gutted 4 of the 12 rooms in the adjacent data center. And they had to turn off not just that data center, but the other 2 data centers close to it. Netcraft estimated this disaster accounted for about 3.6 million websites being knocked out over 464,000 domains. A lot of them were in the French county code top level domain .fr, so it was pretty bad. One of our customers was running a cluster that was partially held in that building. And so out of a 30 node distributed NoSQL cluster, 10 nodes suddenly became unavailable, and you can probably see why. Other than a brief blip, the ScyllaDB cluster continued working seamlessly. Load on the remaining online nodes rose from about 25% for the outage to about 30% 3 hours later. Our customer had just lost 10 server nodes out of 30 in total, but the remaining ScyllaDB database cluster was capable of rebalancing itself and handling that load. Plus, because ScyllaDB is a data center topology aware system and kept multiple copies of the data geographically distributed, their database kept running with 0 data loss. So they lost no data and very little time, if not no time. This can happen. Hopefully it doesn't happen to you. But what can we do to make sure that this kind of resilience is within your hands too? It all starts with the low-level architecture of ScyllaDB. So briefly, we're going to go back in time a little bit to understand the origins of ScyllaDB and where we came from. We began by a Cassandra rewrite, and we embraced the Cassandra design. Cassandra defines a token ring, which is like a single array that's just wrapped around, and every node gets a token range of its own. When you add nodes to the cluster, then one of the existing token ranges gets split and contributes a portion to the node, which happens a little bit randomly. It's quite convenient, and every time you get another node, you split this token ring, which means you can host hundreds of nodes in parallel. And of course, this means it's a no master approach. There's no central coordination. You can just add nodes. But the disadvantage of that is that you can only add and remove nodes one at a time. Otherwise, you'll get this consistency of metadata problem. And since there's only one token range per node, you don't get great data distribution. Cassandra token ring was enhanced in 2012, and they added vnodes. These are virtual nodes, and so it's pretty much the same algorithm, but every node can now host up to 32 or 256, depending on the configuration of the same ranges. It's a simple improvement. Data distribution gets better, but there's also disadvantage to this approach if you need to scan. If you've got big tables, that's good. If you've got small tables, the penalty can be very high. And it's also a problem for things like secondary indexes because they're only local. But now we come to ScyllaDB. This was invented in 2014 and following the Cassandra design. So we embrace the vnodes. We embraced the vnodes. We also have shards, as you can see on the left-hand side, that comprise a cluster. Those shards have vnodes. and they are allocated per node on node creation time. Every node has the same amount of shards as the same amount of vCPUs. So we need to map vnodes and shards as they need to coexist. This gives us a whole nother level of complexity just to be able to deliver that no master shard per core approach. So our initial design on how we would map the vnodes to these shards was simple. Initially, we just split it right? Exactly as you can see here, and as simple as that. Now, the advantage of this is that it's pretty simple. Every shard owns its own data set, so there's shared nothing between the two. The problem is that when you allocate big chunks to every shard, it could be that the differences between the shards will be as big as you can see here. Also scanning, since we scan first the vnodes and then the shards, it again adds more complexity. And this made our life complex. Plus, one of the main disadvantages of having metadata without transactions is that we can only add one physical node at a time. I'm going to come back to this idea a bit later on to show you how we fix this problem. There were some improvements over the years to shards, but I want to skip to where we are now. And this is exciting because our most exciting recent release has tablets enabled, which changes the paradigm of this infrastructure completely. Scylla tablets are pretty sophisticated. So a Scylla tablet, you can think about it as a small range of keys, tokens, up to about 5 gigabytes. A Scylla cluster with terabytes and even petabytes will host tens of thousands or hundreds of thousands of tablets in a cluster, potentially. It's dynamic, so it's per table, and those tablets are assigned dynamically to a node when the node joins a cluster. It has 0 tablets, no token ownership, and dynamically, as the data set grows, then more and more tablets are being created. Every tablet is a full log-structured merge tree, so it has its own SS tables, its own compaction states, its own mem table, and so on. So if you have a small table, initially a table is created only with a single tablet. But you can just create a single table with a single tablet, so scanning it is trivial. And even if you have a big cluster with lots of hardware in it, if you create a single table, then it will be populated with a single tablet, and that tablet will be assigned to a single shard as before. So it will be very efficient to scan or retrieve that single table right from the word go. We fixed some of the low-level issues with the last implementation of the Cassandra token ring. Exciting. But we're focused a bit on resiliency here. This is what this talk is about. So how does tablets help with this? Elasticity is a great part here because tablets are replicated, and they are replicated as other tablets on other nodes, which means that if you want to deal with a failover event or a change in your cluster and cope with that change, so for example, from 4 virtual CPUs to 2 virtual CPUs dealing with some sort of event, then the system will just need to load balance to the new state. And that'll be relatively simple because our granularity is tablets now and not mixed ranges. How is this done? Well, we have a tablet scheduler. A protocol determines which nodes will run the scheduler, and the schedule state is also maintained through the Raft protocol. The scheduler makes thousands of scheduling requests every period, and multiple tablets can change their state, as you've just seen. Usually tablets will undergo one state change at a given period, and that can be migration to another server, it can be repair, it can be backup, it can be more. And this is what the scheduler does in order to come up with the best optimization in terms of its load balancing. You can see how this makes elastic topology really simple compared to the token ring. So we mentioned a few things there, and I wanted to make sure that we're all on the same page, given that we're talking about cluster design and HA events. To ensure no single point of failure, data is replicated. And replication means that obviously we're storing copies of data on multiple nodes. This means that even if one node goes down, the data will still be available. This means that you can ensure this reliability and fault tolerance. But how many copies do we need to take? Well, the number of copies of the data is defined by the replication factor. You'll hear this referred to as RF level. So a replication factor of 3, or RF equals 3, means that 3 copies of the data is stored at all times on the cluster. Depending on the level the RF user sets for the key space, the coordinator will then share that data with the other nodes called replicas to create copies of the data for fault tolerance. Connected to the RF level is the consistency level. Consistency level is the number of nodes that must acknowledge a read or a write operation before it's considered successful. In the case of a write operation, for example, with CL equals 3 and RF equals 4, for example, only if at least 3 out of the 4 nodes the data is written to send an ACK back to the coordinator node, will an ACK for a successful operation be sent to the client. A simple majority needs to agree on what the right data to send back to the client is. But regardless of the consistency level, a write is always sent to all replicas, as set by the replication factor. Consistency level controls when a client acknowledged, not how many replicas are updated. For data to be successfully written or read back from the client, a sufficient number of nodes need to agree on the correct state of the data. And while there might be a default consistency level set for the client, Scilla allows each operation, each read or write, to have its own consistency level, which is really cool. And we call this tunable consistency. And it's used a bit later on. So what levels do we have for consistency? What could you choose? If we have a setup with multiple data centers like this, Scilla allows you to tune your queries for required consistency. Consistency level all, for example, is simple, but it has the lowest availability because it's going to ask every single replica in your entire DC set. You've also got each quorum. This requires a majority from each of your data centers. Quorum requires a simple majority from all nodes across your data center, so some failure is possible here. But local quorum allows you to query just within the same DC, and there are pros and cons to all of these levels that you can choose to match your use case. So let's talk about these queries for a moment. You've seen how consistency level and RF levels can affect the consistency of your queries, but how reliable are they? How much can you rely on them to make sure your queries are responded to? The answer lies in driver settings, but let's review a quick concept first: query idempotence. A query is idempotent if it can be applied multiple times without changing the result of the initial application. Specifying that a query is idempotent increases the chances that it will be retried in case of failure because it's much safer. These queries can be retried in situations where retrying non-idempotent queries could be dangerous. So what settings should you use in your drivers? Well, the most obvious thing is to retry upon query failure with your client, right? Makes sense. So after query fails, the driver might decide to retry it based on its retry policy and the query itself. And you've got 3 default policies. Fall through retry policy. This doesn't bother really doing anything, just never retries, which returns all the errors straight to the user, but it's good to know. The default retry policy set is might retry if there is a high chance of success based on what it understands of the cluster. But you've also got a clever one called downgrading consistency retry policy. So this behaves as the default one might, but also in other cases, it reduces the consistency down to a level where it might get success, utilizing the eventually consistent nature of the distributed architecture here. When requests fail, it's natural for users to want to retry the requests. However, if the request fails due to overload conditions, if you do retry that request a lot, it can make the situation much worse. I mean, the server is still processing the old request, and when the new retry is attempted, this makes the server process both requests at the same time. The server, which was already loaded, is getting worse. It's got more to do, and so it gets slower, and then you ask it to do something else, and it gets slower again, and it's starting to go wrong. So there's this concept of speculative query execution. This is an optimization technique where a driver preemptively starts a second execution of a query against another node before the first node has replied, and then it utilizes the first answer it gets back. There are multiple speculative execution strategies that a driver can use, but we suggest you use this with care because we don't want to overload any of the shards if we don't have to. Simple strategy: simply starts another query execution after a certain amount of time. So I haven't got a response. Let's just try another one, see if I get a quicker response. But the driver can also utilize the latency percentile setting to say, is that host, what's the latency on this specific host? Perhaps I should try another one based on the node which isn't maybe quite so busy. But there's also speculative retry at the server side, because of course we've got replica queries that need to come back, and when a replica is slow or unresponsive, this can be very useful. However, be careful with your settings here. You don't want to overload a shard, continue to overload its replicas, and cause that domino effect to slow the entire cluster down. If you utilize this equation, looking at the average latency with the replica latency and the cross-node round trip time, you will be fine because you've set the settings to be above that. It's not going to have that effect. All right, so the core of ScyllaDB protects the queries, they're retrying, but how do we reduce latency at the driver level to make sure we address any HA events we might have? So all ScyllaDB nodes and shards are equal in importance and are capable of serving any read and write operations. We call the node which handles a given read or write request a coordinator because the data in the cluster is replicated. A single piece of data is usually kept on multiple nodes, specifically in case one of them catches fire. The coordinator has to contact multiple replica nodes in order to satisfy a read or a write request every time. So clearly we can see that it's desirable that the coordinator is also a replica. In such a case, the coordinator has one less node to contact over the network, and it can serve this operation using its memory and or its disk. But this reduces the overall network usage and reduces the total latency of the operation. This is a concept called token aware. It knows which node to go to. But similarly, it's also best if we could send a request to the right shard, which is exactly the right vCPU that is handling that piece of data. Although when you choose a wrong shard, the right one will be contacted to perform the operation, it's still more costly than using the right shard from the beginning, and it might incur a penalty in the form of higher latency. And this is absolutely equivalent with tablets in the new architecture. Choosing the right shard is called shard awareness. And usually when doing common operations on singular partitions using prepared statements, the driver has enough information to calculate the token of the partition, because then based on this token, it's easy to choose the optimal node and shard to choose as that coordinator. But we're in tablets now, and ScyllaDB maintains metadata about the tablets in the tablets themselves. The tablet contains information about which table each tablet represents and the range of data it stores. Each tablet contains information about which replicas hold that data within the specified start and end range. So in the case of tablets, the client learns the routing information lazily and updates it dynamically. So for example, assume the driver wants to execute a query. The driver will make a request to some random node and shard in the cluster. And this initial request is just guessing, so it might be incorrect node and shard. But all the nodes know which node owns which data. Even if the driver contacts the wrong node, it will forward the request to the correct node. It will also tell the driver which node owns that data, and the driver will update its tablet metadata to include that information. So then the next time the driver wants to access data on that tablet, it will reference this tablet metadata and send the query directly to that correct node. So it learns as it goes along. So if the tablet containing the data moves because a new node is added or some event has happened, the driver will continue sending statements to the old replicas, but since at least one of them is not currently a replica, it will return the correct information about this tablet. There's a great benefit to this approach in that the driver doesn't have to store metadata about all tablets, and ultimately this allows a very fast startup of the cluster, also when new nodes join. So when using ScyllaDB, it's more important than ever to use ScyllaDB shard-aware and now tablet-aware drivers instead of the old Cassandra drivers. The existing drivers will work, but they won't work as efficiently. And this will give you a nice throughput and latency boost. But we're missing an important part of the architecture picture here, load balancing. There are a number of options to deal with the results of an outage and to maintain performance of your cluster. One of them is called heat-weighted load balancing. So with time, a ScyllaDB cluster adapts to an application's behavior, which is really cool. Given a steady read-mostly workload, for instance, after initial warm-up period, all the nodes will have their caches populated with a working set, and that workload will see a certain cache hit rate, and you'll enjoy a certain performance level of throughput and latency for that cluster. But what happens if one of the nodes loses its cache? For example, this is not uncommon. Rolling upgrades or an HA event could make this happen. Balancing the work naively among the nodes can result in overloading of the cold nodes, those with the empty caches, let's say, and therefore the entire cluster has degraded performance, and you'll see latencies go up because of this. So the solution is the idea of heat-weighted load balancing. Let's give the cold nodes less work. But that presents us a slight problem, because how much work, therefore, should we exactly give each node? When a coordinator chooses the replicas to send requests to, it should send fewer requests to the replica with colder cache, because that'll be slower, but how many fewer? You can't avoid completely sending requests to the slower cold node, because otherwise it will be cold forever and it will never be used for the request. However, the reason for a cold node becoming overloaded is that it's getting a lot of cache misses due to its cold cache. And each of those requests requires disk operations, and the number that a node can do of those is limited due to the sharper core architecture. So our goal is to send requests to each node at a different rate, calculated to achieve the same cache miss rate on all nodes. So, for example, if one node has a colder cache with twice the miss rate, as a second node, we should send the first node half the requests we send to the second node, so the cache miss rate will be the same on both. There are some equations we can use to understand this in more detail, but this is the idea to bring up a cold node and keep the latency of the entire cluster down. But what other algorithms do we have for load balancing? Simply, there's round robin. This should be used when all of the nodes are located in the same data center to avoid unnecessarily sending queries to remote nodes, which may cause high network costs and higher latencies. But the randomness of this algorithm makes server-side caching maybe less efficient, so it's good it works well for simple deployments. But we have a data center aware round robin as well. This equally distributes the queries to nodes in the local data center. It won't use nodes in the remote data centers unless all nodes locally are unavailable as well. We also have slightly more advanced algorithms. There's latency awareness. So this tracks the latency of queries to avoid sending new queries to poorly performing nodes. You need to use this with a token aware policy, of course. This will reduce the latency of the requests by avoiding that extra network hop we previously talked about. And of course, now we're fully aware of what a token aware load balancing algorithm is. Direct to the node that holds the shard of that data. But what else, you ask? Let's allow Scylla to understand the racks it's deployed on and prefer local racks and work up for there. This in itself can significantly reduce network costs across zone. And there's even random two-choice now, although this is currently an open PR. But this looks at how many in-flight requests each host has and to choose the best one at that moment to get the best response. And let's finish this by noting that Scylla also has zone awareness. And this is important to save network costs with cross-zone traffic charges. Our favorite cloud providers do charge you for cross-zone and cross-region at different prices. But the trade-off for this is that best practice in ScyllaDB says your replication factor should be at least 3, and your cluster should be a multiple of 3 nodes, which means you have to be careful where you're going to choose, what you're going to choose in terms of your cluster size and where you're going to deploy them. In the end, it's best to have a choice, and Scylla gives you a choice for load balancing in spades. ScyllaDB recently completed the transition to strong consistency for all cluster metadata. What does this mean? Well, this transition involved moving schema and topology metadata to Raft. Raft implementing a centralized topology coordinator for driving topology changes and several other changes related to our commit logs and schema versioning, authentication, and some of the other aspects of database internals. We don't have time to get into the details here, the nitty-gritty details, but it's important to understand why this is so important when considering the reliability and scalability of your cluster. Quick recap of what this consistency idea is all about here. And that is that it's a model of concurrent interaction between the client and the database. Strongly consistent system when interacting with a client guarantees the freshness of its current state. And eventually consistent is allowed to provide the user with not up-to-date data, but eventually reconciling these changes into a single state. Eventually consistent systems can accept writes to nodes partitioned away from the rest of the cluster, whereas strongly consistent systems require a majority of the nodes to acknowledge the operation. So a trade-off between strong and eventual consistency is in requiring the majority of the participants to be available to make progress. Apart from storing the user data, the database maintains additional information about it, which were called metadata. And this is topology of the nodes, of data distribution, and schema, which is table format information. So a while ago, we realized in Scylla, there is little business value in utilizing the eventually consistent model for metadata. Metadata changes are infrequent, so we don't need to demand extreme availability for them. Yet we want to reliably change the metadata in automatic mode to bring elasticity, which is hard to do with the eventually consistent model underneath. So with all topology and schema metadata now under Raft, ScyllaDB officially supports safe, concurrent, and fast bootstrapping. And this is how we can have dozens of nodes now start concurrently within a Scylla cluster. Rapidly assemble a fresh cluster, perform concurrent topology and schema changes, and quickly restart a node with a different IP address or configuration. All of this is now possible. And this is what I referred to way back at the start of this presentation. This is really exciting for what it means with the flexibility of your ScyllaDB clusters. Now, there is much more to discover here. And if you want to know more about Raft and how it's implemented, I'll point you to my colleague's presentation entitled Majority Loss when a leader fails. There is a lot more great information from Konstantin here. So, what lessons have we learned? Well, the first thing I learned from this presentation was that your deck needs to be resilient. So the RF of my lessons learned presentation here was 2 because I definitely lost one copy of this whilst creating it. But in terms of Scylla, we've learned that ScyllaDB's resilience keeps your data safe and your system running, even in the face of severe outages. From its core architecture to the query consistency levels you can define, tunable query level consistencies, to the client drivers allowing different retry capabilities, to the topology elasticity that it's got with resilience built in from its tablets, all the way through to the consistent metadata delivered by Raft. ScyllaDB helps you keep your business running and your data safe. Thank you very much and enjoy the rest of Monster Scale Summit.